Okay, off we go. So here's a new topic for today. We're talking about more derivative stuff, frankly. Now you're going to notice that we jump up here to section 3.1. We've been in early chapter 2. So this is just a quick zig. There is a little bit about derivatives of parametric curves that I find very useful to have done before I get into the late chapter 2 stuff. So I'm going to zig up into chapter 3 real quick, do what I need to do, and then we're going to zig right back into chapter 2 in just a couple of minutes. Okay. All right, so we've talked about parametric curves before, and keep in mind if you have a parametric curve, really what you're talking about is position as a function of time, and so all of your coordinates are just functions of time. Okay. All right. So let's just notice what does the derivative matrix look like. And the derivative matrix, well, there's only one input variable. And keep in mind, input variables, when you're looking at a derivative matrix, input variables correspond to columns. So you notice here all these derivatives in this first column of the derivative matrix, they're all derivatives with respect to t, which is the only variable, and so this is the only column in the derivative matrix. Okay. And then you look at that and realize, and we've made this observation before, well, that's really then just the derivative of the vector-valued function. It's the derivative of the x vector with respect to t, just one coordinate at a time, right? Okay. Well, last time we found ourselves at some point looking at this, and I said, yeah, it's the velocity, and nobody called me on it. I think it's a pretty believable assertion, but I want to go ahead and flesh that out. I didn't do it at the time because we had a lot going on at the time, and I think it's a pretty easy buy anyway. But let's flesh out in what sense can we feel justified calling this the velocity. Okay, well, derivative. Here's how you compute derivatives, right? Old news. Single variable calculus, definition of a derivative. And let's just kind of break it down. I mean, what have we got up here? We've got a position at some time t, and then we've got here we have position at some later time, h seconds later perhaps, right? And so we're just a little ways further down the curve. The numerator then, let's see here, I'll use this. The numerator is just the difference of those, then is that vector. And then, of course, don't forget to divide by h. Dividing by h, I'm representing it here as if h is a little larger than 1. We get a slightly, therefore, shorter vector. And there's the thing we're taking the limit of. So if you think about it, what happens as h approaches 0, and keep in mind that's what we're doing. We're taking the limit as h approaches 0. Well, as h approaches 0, there's several things that happen. On the one hand, this point here is it's going to move down the curve and get closer and closer to that starting point. Then another thing that's going to happen is this difference vector, therefore. This difference vector is going to be getting, let's see it's hard to draw like that. But these difference directions, I'll say, are going to be getting closer and closer to tangent to the curve. Right, now we're not looking at slopes. Nobody said slope. Right? But it is kind of smacks of an old argument that you all heard in single variable calculus, that these secant lines are getting closer and closer to tangent lines. It's just that, again, we're not looking for slope, so it doesn't have anything to do with slope, but what we can say is that the direction of this limit vector, right, this limiting, the derivative that we're trying to understand here, this x prime, that eventual limit, the direction is the direction the curve is going, because its direction is tangent to the curve. Okay. And now let's talk about the magnitude. How long is it? Well, and kind of eyeball this and see this numerator again is a vector. It's a displacement vector between 2 points on the curve, and its magnitude then, keep in mind, if we're interested in the magnitude of the velocity, Right? We only need to understand the magnitude of the limit, and so therefore just the magnitude of the numerator. That magnitude is distance. It's how far have we traveled? Distance, right? And it's distance, though, per unit time, and well, that's speed. This is just a straight up computation of instantaneous speed. So if you think about it then, what we've got is the single variable definition of a derivative gives us a vector pointing in the direction of motion whose magnitude is the speed. Where have we heard that before? Probably first day of class possibly even first day of class of Math 218. Because this is a early example of what is a vector and what do vectors represent, and this is velocity. So there you go. So again, I kind of waved my hands at this last time, but there's a more detailed discussion that the derivative of position with respect to time is velocity. Okay. All right. Now, similarly, the second derivative is acceleration. And again, I think that's not news. Looks very familiar, I hope. Okay, so a couple of examples. Suppose we are given, let's just say, velocity as a function of time. And first question, how do I compute acceleration? Well, this is an easy one. You're given velocity. You want to compute acceleration. We know from the previous page, it's just a derivative of velocity, right? So we're going to take the velocity, and acceleration is the derivative of that velocity. And a little bit of calculus, and boom, there you go. Everybody happy so far? Okay. All right. Next part of the question, you see, says, what is position now, given velocity? Again, well, so again, there is a relationship. If you know the velocity, position is the antiderivative of velocity, or I should say that more carefully. It is an antiderivative of velocity, because velocity is the derivative of position. So I hope everybody's with me. This is all tracking very heavily analogous questions from single variable calculus about using velocity to sort of reverse engineer to find position. Okay, so we're going to take some antiderivatives. Antiderivative is computed one coordinate at a time, just like you'd think. And a couple of easy antiderivatives to compute there. That's that one, and that's that one. Don't forget your integration constants, though. And now, the way I've written this, you'll notice, I could have written one integration constant on this line and another integration constant on this line, maybe call them C1 and C2, something like that, right? But then I'm just going to pull them out and call them the C vector, because after all, it's a vector with coordinates C1, C2. Okay, how are we doing? Here's where a lot of students make a mistake. A lot of students have either been misled through careless experience or something to think that the integration constant is always the initial condition, and that's just not true. It's just not true. I can tell you why students have been confused to think this might be true, but it's absolutely not true. First of all, let's compute the integration constant the right way. Then I'll come back and complain about the misinterpretation. We have here position is this function. And here it is again, in which I have plugged in t equals 0 into all three parts. That's all I've done for this second blue circled equation. Same exact equation, I've just plugged in t equals 0. If you think about it, at t equals 0, that's kind of the point of what this is. This is literally x of 0. It's given. So that's why we get 5, 6 there. Right? Whoops. Let me delete that. And let's see here. Then what about this term here? Well, I'm just literally going to plug in t equals 0 and evaluate, and that turns into 3, 1. That's just a little bit of arithmetic. And then finally, c, that we are trying to determine. Can't do anything with that yet. Okay, but now that I've plugged everything in, you can just solve for C in this equation. No problem. There it is, 2, 5. And you see it's not the initial condition. Everybody happy? So where does this mythology come from that so many students inadvertently think that, it's always, every high school question I ever did, these were always equal. Where did that come from? It comes from the following. And that is that a lot of high school teachers are a little careless about examples that they show. And for example, if your velocity is a polynomial, you think about it. If that's a polynomial, then over here you're going to have, what happens when you take the antiderivative of polynomial? You get another polynomial, but in which there are no constant terms. You get a polynomial where every term has a factor of t in it. And if you take t equals 0 and plug that in to an expression that has factor of t in every term, right, you're going to get 0. And so you get 0 there, and in such a case, then you can see, sure, indeed, you would get the integration constant being the initial condition. And you also see, I hope, that this is absolutely unrepresentative, and it's a coincidence, total coincidence of the very narrow category of examples that, in some cases, some high school teachers might not think of the importance of branching out from. So, if these are polynomials, then you're going to get this unrepresentative coincidence. Okay, so how are we doing? Is everybody on board? All right. Okay. And real quick, I want to point out that we are computing antiderivatives here. We're undoing the derivative, thus the term antiderivative. This can be related to integrals. And integrals is something we're going to talk about later. We're not really quite ready to get into that whole discussion yet. But there is a relationship between antiderivatives and integrals, but make sure not to overconflate. I think it's valuable. I think it's particularly important in this case to think of this as anti-differentiation, because that's really what we're trying to do. You can take the point of view that we're trying to add up a bunch of little things, but then you've got to be careful about exactly what are these little things that we're adding up. And most importantly, again, a lot of people see antiderivative, they think integral. When they see integral, they think area under the curve, right? But in this case, absolutely not. There's just nothing in this story that says anything about area under curves. We're just undoing the derivative to get position. It's got 0 to do with area. Yes?
Is there a different geometric interpretation of this that isn't area under the curve?
Yeah, so you can look at this equation right here, right? And if you look at v times dt, and let's sort of think about that for a moment, right? What happens when you multiply a velocity times a little small piece of time? And velocity times time gives you a displacement, right? And so what we've got here, you can think of this as a little displacement, and you can think of the integral as, well, we're adding up a bunch of little small displacements, and when you add up a bunch of small displacements, you get the overall displacement from which you can infer position. Right? So absolutely, that's kind of a geometric point of view on it, but it's also kind of unnecessary, right? Undoing the derivative is really all we already know that what we are taking the antiderivative of is the derivative. So it's kind of make work in some sense. Is that satisfying? Okay, yeah, it's a good question. Okay, all right. Okay, there's a couple of other things in section 3.1 that I want to note, but a lot of section 3.1 you're going to note on the content syllabus. You are excused, right? It's excluded material. Again, look at the content syllabus. Don't forget that far right column that notes which parts of the book you are officially excused from. And there's a bunch of stuff in section 3.1 about Kepler's studies of planetary motion, and you're not responsible for any of that. Again, if you're amused, if you want to, go ahead, but it's not required. Okay, that said, in that discussion, hidden inside of that discussion, there is some pretty useful stuff. In particular, we have two kind of product rules here for parametric curves. And so I just wanted to point these out. Again, they're exactly what you would think at a glance. But these are things that you should know, even though they're kind of buried inside of that Kepler stuff that you're excused from. Okay. All right. Okay, so back into chapter 2. Talk about the chain rule. Y'all remember the chain rule from single variable, I'm sure. I'm going to give you a point of view on the chain rule from single variable calculus. By the way, you're going to notice, I've probably already done this a few times, very often what I like to do to explain multivariable calculus ideas is to first go back to single variable calculus and take a certain point of view on the single variable version. Maybe a different point of view than what you've seen, but if you take a certain point of view on the single variable version, then it will very naturally generalize or extend to the multivariable version. And so very often that's what I'm doing. So that's what I'm doing here. I know that y'all know the single variable chain rule, but I want to take a certain point of view on it so that I can step it up. So here we go. So a point of view on derivatives, single variable derivatives. That the derivative is a relationship between input changes and output changes. Right? The derivative is the thing that you multiply by the input change to get the output change. And in here I'm writing that as rate of change. Okay, so I hope that this isn't news to anybody. And again, reminder, one of the foundational ideas that I proposed about, how should you think about derivatives? When we first started talking about derivatives last week, was it's a relationship between input changes and output changes. And that's the point of view we're taking here. We've got an input velocity, right? An output velocity, and, well, the derivative of this function is what relates them. So, is this the main way that you've thought about derivatives in the past? Well, probably not. No, that's fine. But this is the point of view that I want us to take for this discussion because it's going to be most useful. Okay. Is everybody happy with this? All right. Okay, so let's look at now a composition of two functions. So you'll notice here I have a function. Y is a function of x. Right? The y is the output variable, x is the input variable. Okay. And then now you'll notice over here I have a second function. This thing y that comes out of f is the thing then that's going to go into g. So again, composition, sort of you might say concatenating two functions, I suppose. But anyway, the thing that comes out of f goes into g. G now, another function. Y is the input variable and z is the output variable. Okay. And what I'm going to do is I'm going to take our idea of what is a derivative and just write it down as it applies to each of these functions. So here you go. For f, x is the input, y is the output. So the derivative of f is the thing that you multiply by input velocity to get output velocity. It's just the exact same idea of derivative we talked about above. Yes?
So x prime and y prime here, those aren't derivatives.
They're derivatives with respect to time.
Okay.
Yeah. So velocities, in other words. And you may recall, I have this kind of preference for thinking about changes as velocities, because then they're instantaneous and I don't have to go through that whole rigmarole about approximations and what does a good approximation mean. It's all instantaneous, and so it's all exact. Yeah. Is everybody happy? Haven't really done anything yet exactly, but there's single variable interpretation of the single variable derivative as pertains to this f function. And now, of course, we can do the same thing for this function. And, well, we have a derivative of g, dz dy, and that's a relationship between input change and output change, aka input velocity and output velocity. Again, the exact same, it's just single variable, just what I had above. Okay. So what I want to do, though, now is apply this idea to the composition. The composition, keep in mind, is both functions kind of stuck together. So x goes in, and then the composition happens, which is a plug-in followed by another plug-in. Sure, whatever the composition does, but altogether what comes out of the composition is z. Right? So x is the input, z is the output. So that derivative is dz dx, and that relates input velocity and output velocity of that function. Okay, so all I'm doing is writing down what the single variable derivative means, but now I have the opportunity to do some clever plugging and comparing, and specifically, I'm going to take this equation here, I'm going to plug it in for that y prime right there. So I'm plugging 1 into 2, which makes 2 turn into that. Right, just plug it in the green, which is there, you might say. And then now let's compare that with this third equation that we have. Let's see here. I'm going to compare that with that. And you can see what we've got is, in both cases, we've got something times x prime equals z prime. Something times x prime equals z prime. So those two things must be equal. The two things that you multiply times x prime to get z prime, those two things must be equal. So there's our chain rule, our single variable chain rule, and this is an argument for how to get it. Now, if you just kind of look at the screen here, it's tempting to say, wow, there's a lot of equations and arrows, and oh my gosh, that looks complicated, right? The easy way to think about this, though, and what I encourage y'all to do, this is, we've got a certain amount of algebra to make this all precise, but interpret it as follows. Ultimately, what the derivative of f is doing, it's multiplying by a factor. You're multiplying by this thing called dy dx. Velocities get multiplied by dy dx. And then what does g do? Well, it multiplies velocities by another factor. And altogether, after multiplying by whatever that factor is and whatever that factor is, altogether, notice you've multiplied by a product. Because you multiplied by a number, then you multiplied by another number. Altogether, you multiplied by the product. So, altogether, of course, is just representing what the derivative of the composition is. So really, this is kind of the observation that if you multiply by one number and then you multiply by another number, then you've multiplied by a product of those two numbers. So pretty intuitive, I think, when you think about it that way. Is everybody with me? Okay. All right. So all single variable calculus. Why are we doing this? By the way, let's observe. I think this is a nice observation. We were looking at a composition, and then 2 seconds. And then after once we were looking at a composition, we took a derivative, and what we got was a product. So this is kind of what happened. The act of differentiation turned a composition into a product, and I think that's a nice sort of a quick verbal summary of the result. Yeah, you had a question.
Where you had dz dx x prime is equal to z prime a little bit soft.
Yeah.
If we didn't have y, but we were just given dz dx, we wouldn't need it. Like dz dx contains dy dx.
Dz dx, you can think of that as being a product of two factors, one of which is dy dx.
And
That's
if we
true.
were just given dz dx, we wouldn't have to know dy dx. We wouldn't have to go through the process.
It depends on what you're given and what you're looking for, right? So right now, I'm not approaching this as here's what I'm given and here's what I'm solving for. I'm just approaching this as I'm just making observations, and the result is I have a relationship between quantities. So what I'm going to do with this result, well, sometimes I'll be given these two things and I'll be solving for this. Sometimes I might be given these two and I'm solving for that. Or who knows? But this is just a general truth, and how I use it depends on the context. Is that satisfying?
Yeah.
Okay, cool. All right. Good. Okay, so all single variable calculus. Now what I'm going to do is do the exact same strategy to derive a very analogous result for multivariable. And here, first, the observation about what a derivative is in a multivariable setting. A derivative is a relationship between input velocity and output velocity. Right? That relationship. What do you do to the green vector to get the yellow vector? Hey, you multiply by the derivative matrix. Derivative matrices turn input velocities into output velocities. Right? And note the strong analogy. Back here, a derivative was what you multiply by input velocity to get output velocity. Here it was a scalar. Here it's a vector. But it's, in some sense, the same kind of thing is happening. Everybody see the analogy there? Okay. So, okay, so we're going to apply this to a composition in sort of three different ways. So first of all, notice I have a composition here in that we've got this function f from the x, you might say the x plane into the y plane, right? And then we've also got this function g from the y plane into the z plane, you might call it. And we can consider the composition of where I start with the x inputs, apply f, then apply g, the output of which is a z vector. So we got three functions, just like in single variable. In each one, the derivative is a relationship between input velocities and output velocities. Right here, this matrix, df, multiplies by x prime to give y prime. For this function, dg, what you multiply by y prime to get z prime. And for this composition, the derivative of that composition is what you multiply x prime to get z prime. So, three applications of the same idea that derivatives multiply input velocities to get output velocities. Is everybody still with me? Okay. So, well, again, I'm going to plug 1 into 2, right? This 1 is a formula for y prime, you might say. I'm going to plug that in to there, which gives me this. Right? So, take this formula for y prime, plug it in there, like so, which, of course, again, the y prime is that thing right there. And I've got a matrix then times a vector, and associativity tells me I can reinterpret that as a matrix times a matrix, pause, times a vector, right? So associativity says you can kind of pause wherever you want in that product. And then again, comparing that to the equation above up here, comparing this to that, what I multiply by x prime to get z prime, those two things must be the same. And here is our multivariable chain rule. Notice again, it is differentiation turns a composition into a product. We had a composition of multivariable functions. We get that the derivative is a product of the individual derivatives. It's just that it's now a matrix product because the equations we had been working with, with which we've been copying the single variable argument, are matrix algebra. Okay. How are we doing? All right. Okay. Real quick, notice that I did this example with 2 dimensions in just because it's easier to draw the pictures, but there's nothing really about the fact that this was 2-dimensional that was essential in this. Here, I'll tell you what, I'll make it 3-dimensional okay, now it's 3-dimensional. Right? Same argument. Now they're 3-dimensional. Right? Or if you want to have 2 to 3 and then 3 to 2, also fine. Right? Any dimensions work. It's because these are vectors in general. Okay, see an example. One other thing, little detail. Got to talk about these derivatives and where they're evaluated. So starting with looking at F, the thing that relates input velocity to output velocity it's the derivative. Yeah, sure. The derivative, but evaluated where? At which point am I going to plug into this matrix df to get the thing that multiplies by this vector to give me that vector? Well, evaluated, of course, at the point where I am. Right? Don't forget that when I say I want to relate this velocity to that velocity, it's that I'm at this point and moving with that velocity. And then I want to keep track of where my image is going and what is that image velocity. So this point is where it's all evaluated. It's the point where you're at, from which you're moving with that input velocity. That's where it's evaluated. Fine. And it's just you just have to notice, though, that when you think that through, as pertains to this, where we've got input velocity y prime and output velocity z prime. Where am I? What is my location at which my derivative matrix is evaluated? Well, I'm at that point. It's not A. It's of course it's not A. A is way over here. A is in a different universe, right? It's in X world. We are looking at this function g, which takes inputs y, and so the derivative matrix is it's evaluating where you are, which is y, which is f of A. So, thus, the f of A right there. Does that make sense to everybody? All right, so let's apply the chain rule. Here I've got a scenario described. I've got this f function that takes x variables and gives y variables. I've got this g function that takes y variables and gives z variables. So this is set up just like on the previous page, except you'll notice, while there are still 2 x variables, there are now 3, switch colors, 3 y variables, and also 3 z variables. So the dimensions are a little different, but doesn't matter if we're taking a matrix point of view, as we are. Okay, so here is the chain rule. And now, so you say, well, we got to figure out I need to know some of these matrices. I can't just pull this out of a hat. Where am I going to get these matrices from that I'm multiplying? And notice that they're given very conveniently, right? So df at the point 1, 2 is given. There it is. And let's see here. What else? Let's see. We need dg at f of 1, 2. I am not immediately given dg evaluated at f of 1, 2 until I notice that, here's the thing. F of 1, 2 is 3, 1, 0. So in fact, yes, I am. It just didn't look like it at a glance, right? But we are given dg evaluated at f of the starting point 1, 2 because that f is 3, 1, 0 at which I'm given dg. Okay. All right. So this matrix is dg of f of A, you might call it. So, so there we go. We win. We were again asked to compute, in this example, we were asked to compute the derivative of the composition. It is this product of individual derivatives, little matrix multiplication that I'm sure you all remember and are good at. And boom. Everybody with me? So, very nice. Linear algebra, by the way, I'll comment, is doing a lot of work for us here. because there are a bunch of variables that are represented in a bunch of ways, and there's a lot going on. And matrix multiplication just does all the bookkeeping for us and keeps track of the point is, you shouldn't really think about these as two input variables. You should think of this as an input vector. And you shouldn't think of these as three outputs soon to be input variables. You should think of these as a vector, and likewise this final output as a vector. So if you just think about everything as vectors and the relationships between them as matrices, then again it's multiplication. Okay. Now, there is a second part to the question, you'll notice. Second part to the question said compute this particular partial, the partial of Z3 with respect to X1. And here's the thing, we just got through computing the derivative, the overall derivative matrix. And let's see here, I am going to need to zoom out. We want to compute, it says, partial with respect to X1, X1 being as it is the first input variable, means that we're looking in the first column. Right? Remember, there's a very particular finicky structure of how derivative matrices are written down, and input variables correspond to columns. And let's see, we're taking the derivative of Z3, which is the third output variable. And being as the third output variable, we're therefore interested in the third row. So altogether, this particular partial that we want is the element in first column, third row, which therefore is 3. What do you think? Cool. Real quick, a couple of special cases. There's nothing really deep that's going to happen in the next couple of pages, so I'm going to try to do this reasonably quickly. But I just notice if you have a single input variable, t, then some of the matrices are actually simpler than you would otherwise expect. So, for example, the derivative of that, well, there's a single input variable, and so there's a single column, and so that is just a velocity vector, right? And then, well, yeah, but also, let's not lose sight of the fact that the composition also has but a single input vector. And so its derivative matrix has a single column and again represents a velocity. So it's interesting. In fact, you can think of this first function as literally being a parametric curve in Rn. The derivative matrix is its velocity. And you can think of the composition, think about it, you've got position y as a function of time. You've literally got a parametric curve in Rm. And this is its velocity. So, yeah, this little scenario where you have just a single input variable at the beginning is really just, it kind of recovers what we already knew about the derivative matrix. This function, the derivative of that f function, relates input velocities and output velocities. Kind of old news. So, anyway, it's just an observation of what that special case looks like. And here's just kind of a fleshing out. So here is a function, multivariable function, and we've got 2 inputs and 3 outputs, right? And then we've got a story about where we're at and what the velocity is. And let's see, we are currently at the point 2, 1, and then we're moving with velocity 4, 3. So I've got an input location and velocity, and I want to know my output velocity. Well, this is what derivatives do. I have an input velocity. I want the output velocity. Derivative of f does it for us. So input velocity 4, 3. I need to know the derivative matrix, so I got to look at this f function, and I've got to go through and compute its derivative. I've got to evaluate that derivative at the point where I'm at. Various little partial derivatives and plugging in. And so our derivative is this, and then multiply to get the output velocity. Everybody on board? What do you think? Okay. All right. Okay. All right, here's another special case. Again, it's not really any different. This is just a notice how it might look different under certain circumstances. I'm going to continue along with having a single input variable, just t, just one single input variable. Here we're going to further entertain what happens if I have a single output variable. Well, with a single output variable, this function, its derivative matrix, there's only one output, and therefore there's only going to be one row in that derivative matrix. And so the chain rule, again, it just looks a little different. Here we have a single row, and therefore the product has just a single row, but it already had just a single column. The product then is just a single value, and it's dy dt. It's the derivative of the sole eventual output with respect to the sole initial input. Okay. All right. So, and we've already made the following observation, that is that if you have a matrix multiplication where the left matrix is a single row matrix and the right matrix is a single column matrix, then it's literally this times that plus that times that plus that times that. It's literally a dot product. Right? It's a dot product where the thing on the left that you're dotting effectively is, well, if you just notice, it's the gradient vector. And the thing on the right we've already observed is the what you might call the input velocity. Okay, so the special case here is just that, it's still, the derivative matrix relates input and output. It's the same, okay? It's absolutely the same. It's just that in this case, it looks like a dot product with the gradient instead of like a matrix multiplication. Okay, so quick example. Suppose you've got some region of space, maybe outside, whatever, and temperature is a function of position, which of course it is, right? Think about it. There's shady areas that are cooler. There's sunny areas next to concrete that are hotter. So temperature varies a lot. And so with if this is the case, notice this is a real valued function. And if I have an input position and velocity, I could ask, what is the output velocity? And of course, the derivative is what does it, right? The thing that relates inputs to outputs is the derivative. In this case, again, we have a real valued output, and so we're just going to interpret this as the dot product with the gradient. This is the action of a derivative. Dot product with the gradient. And so, so we compute the gradient. Oh, whoops. Colors. There's the gradient. That's just various partials. We plug in the point in question. Right, keep in mind we're at this point. And altogether then, here is your gradient that you dot with. And again, you dot, let's see here, you dot input velocity to get the output velocity that we wanted to find. And there it is. That's the rate of change of temperature that the bird experiences. So notice, again, it's still derivative is what you multiply by input velocity to get output velocity, exactly like we've done in several previous examples, just that now that derivative is a dot product with a gradient. Okay. Okay, now here I'm going to give you now a different point of view on the chain rule, and it's arguably not as clean. It's not as elegant. It's not as general. But sometimes it's really handy. And so here's the idea. First of all, I'm just going to straight up write down the chain rule. Here is the chain rule, matrix form of the chain rule, right? That if you have an F and a G as I have set up there, then these two derivative matrices multiply to give me the composition derivative matrix. So nothing happened. That's just the chain rule matrix form that we've already written down. But let's notice then, if I were to pick out, one of the elements, just one element of the product, and if I want to compute, how would I compute that? Well, it's a matrix multiplication. So I can take whatever row that's in, and whatever column that's in, whatever column it's in, and dot it up, right? And doing so, notice you get this formula, and there's actually something kind of nice about this formula. I'm going to come back and I'm going to say quite a bit more about why we like this formula in a minute. But this formula by itself, it is just one formula. There's no matrix algebra in it. Trying to erase it. There we go. It's just one formula. There's no matrix algebra, and it directly tells you one of the partial derivatives. And if that's all you wanted anyway, and that's sometimes the case. Sometimes you don't need to know the whole derivative matrix. Sometimes you just need to know one partial derivative. And here's a very efficient little single punch this one thing up formula for how to compute that single partial derivative. Okay. All right. Now, before we get to examples and further interpretations, it's really important to notice you absolutely cannot do that move. They show us this in single variable calculus, and for formality reasons, there's issues to be upset about that, and I won't talk about that at all. The reason you can't do it here, though, it's not about formalities. It's that this is wildly wrong. It's really, really wrong to just cancel those things. Let me elaborate. So, for one thing, notice that if you do it, you'll just straight up get the wrong answer, right? So you can cancel those, and you think you're getting that. But then over here, if you were to cancel those, well, now you think you're getting it again. It kind of feels like if you can do that cancellation, wouldn't you get partial zi, partial xj, like m different times? And why isn't there a factor of m over here? So it's just garbage. You can't do it. It does not work at all. The reason that this illusion looks like something that you'd think you ought to be able to do, but you can't, is because of the notation. The way we write this, it looks like a fraction. There's a point of view in some sense, but you shouldn't think of it as being a fraction. You should think of this as being something that we compute as part of a particular scenario. And let me remind you, there's a very particular scenario here. Xj is my variable. When I say partial with respect to xj, that means now I'm going to hold all the other x variables constant. All the other x variables are constant, and I'm going to start fiddling with xj. Xj is going to change, and then I want to see how y1 changes as a result. Well, here's the thing. If you are changing xj, y1 is going to change, but all the other y variables are going to change too. You're literally changing the inputs to all of the y variables. All the y variables are going to be changing. So in this story here, let's see here. In this story, the other y variables, very importantly, are not constant. They can't be. Their inputs are changing. But now if you come over here and ask, well, what's going on in this story? This is a totally different story. In this story, we're taking a partial with respect to y1, which means that all the other y's are required to be constant. These are very different stories. Right? The idea that you would cancel these is kind of like, imagine you're telling one story where there's a character named Bob in this story, and then your friend is telling a totally different story about a totally different Bob. And then you start to make connections between the two Bobs because they both are named Bob. It just doesn't make any sense. You can't do it. That's not how it works. So, anyway, make sure that you don't accidentally do this cancellation. I make a big deal out of this because I do see this on tests far more often than I'd like, and so don't let that be you. You cannot cancel like this. Okay, is everybody good with that? Okay. All right. Okay, so what sense do we make out of this equation other than this comes out of the matrix algebra? But why should this... I'm out of time. Shoot. Okay, sorry. I lost track of time there. So we'll draw the line right there. And on Wednesday, we will start making sense out of this equation and how to think about it other than as an algebraic sort of thing. All right, y'all have a good day.